Okay, so today's module is looking at defining power dissipation over resistances in a circuit or resistors in a circuit. Looking at a formula that we should be pretty familiar with now is power is equal to voltage times current, and solving problems using power, and modeling the rearrangement of P equals VI to solve different values for R and V, or I and R. So we can go through this step by step. So first thing we want to look at though is, so can you verify the formula P equals IV by the units on the right hand side? So when we're looking at verifying a formula, looking at the units, what is the unit we're expecting for power? Power, okay, is energy over time, okay, which we usually say is work done over time. And so the energy for work done is given in the joules, and the time obviously is seconds. So power is joules divided by seconds. So when we multiply I times V together, which is the right hand side of the equation, what we should get is joules per second. So let's have a look at this derivation, and you can pause the video now and you can give it a go for yourself, and come back and see if you can get from IV here to joules per second. That's what we want in this particular case. Okay, hopefully you succeeded there. What we're looking at now is, so the SI unit for current is amperes, okay, and then the voltage is joules per coulomb. All right, so now how we're looking is we needed one extra step, right? We need to get to seconds. And so what we have is we have current, which is measured in amperes, and charge, which is measured in coulombs. And we need one more formula, don't we? And that's the current formula, where is current is equal to, current is amperes, which is charge per time, okay? And so this is coulombs per second. So we can do a little bit of manipulation here. And this is equal to amperes, and we can say that the coulomb then, is equal to amperes seconds. Okay, so following on from this derivation up here, we're going to substitute for this, and what we get is amperes over joules is equal to over coulombs over ampere seconds, which cancels out, and we are left with joules per second, which we know is a watt. Okay, which is power. So this is a good example of how we can use units to verify that the formula is actually correct. Okay, well, taking in the next step, okay, what is a watt? Okay, in fundamental units. So a watt, we just said, is a watt is equal to joules, okay, per second. How fast we're doing work, basically. Now I want you to express that in fundamental units. Pause the video, have a go at the derivation. Okay, what we should be getting familiar with now is this idea that a joule, okay, is equal to a kilogram meters squared seconds to the -2. Okay, it's a force, kilogram meters per second to the -2, multiplied by a distance in meters. And so all we have to do then a watt, if we substitute in for that, kilograms meters squared seconds to the -2 over a second is equal to kilograms meters squared seconds to the -3. So that is your fundamental units for watts. So let's have a look at how resistance affects the power delivered to a circuit. Now remember what resistance does. Resistance lowers current, okay? But the potential difference usually stays the same, okay? And we know that P is equal to IV, and if we have a high resistance, we have a low current, which means that we're gonna decrease the current and therefore decrease the power. Most of the time, the potential difference is kept the same. So here we're going to derive, and so we only want to derive P in terms of V and R. So we're going to start with P equals IV, and we're going to substitute in, for using Ohm's law, I is equal to V over R, and what we get there is then V over R times by V is going to equal V squared over R. And this is exactly what I said. If we do a quick analysis, if we increase the resistance, okay, the power on this side is going to go down because the current goes down. So building on this idea, what we should be able to do is if we had a graph, I'm definitely using a highlighter here, well, I'll change back to a pencil. If we had a graph where we're having a look at power and the effects of resistance, we would have an inversely proportional relationship. And if we linearize that relationship, which we should be getting pretty good at doing, we have power, then we put 1 over R, if it's inversely proportional to, we'd get a straight line. And the gradient of that straight line would be V squared. So I'll just put gradient is equal to V squared. Okay, so power is probably the most practical thing in electrical circuits. We generate electrical circuits because we want them to do work. Okay, and now just looking at this idea of power, power is equal to V over I. I'll just write that up here. Power is equal to IV, or V times I should say. Yep, IV. And we can generate the same work, okay, done by doing a couple of different things. We can either increase the current. If we increase the current, that means that the voltage must go down in order to keep the power the same. But what we know about current is current generates heat, and then energy is lost through heat loss to the outside atmosphere. And we don't want that, especially if you're a power plant generation and you want to provide energy to the consumer. You don't want heat loss in the wires that take you there. Okay, so an electrical grid, what will happen is they will step up transmission. We'll talk about this more in AC currents, when we do AC currents and electromagnetic effects in Unit 3. But step-up transmission means that the voltage is increased. We want to increase that voltage, okay, which decreases the current, which decreases heat loss. So we want low heat loss, okay, because that's energy that otherwise could be used for something else. So over here we have a very high potential difference, very low current, and we can do that different engineering ways. Not as simple to explain to you. One way you would think is if you just increase the resistance, but it's not that easy. But what's also noticed here is then we step it down once we get it back to the industry. And so the industry actually works at a higher voltage or potential difference than what we would in our home, okay? So industries have bigger machines and need to do work faster, and so therefore they want a higher power, so they want a higher potential difference. And so the industry machines require, higher voltages. And then once it gets down to the consumers, the residential consumers, in Australia it's around 240 volts. And then in America I think it's 110, but in Europe it's around 230. So depending on the country, depending on the energy supplier, it'll be different values. Okay, so let's have another practice derivating another formula, but this time we want values for current and resistance to calculate the power in a circuit. So here P is equal to IV. We'll start there, and this time we want I and R are the only two, so we want to eliminate V. So we can do a direct substitution actually straight in for this V value, and we get I times by IR, which is equal to I squared R. So if we want to calculate the power of the resistor, and we have the values for current and resistance, we can then work out how much power is dissipated in that circuit. Okay. Usually we use this because this is what we can measure, right? We can measure current and we can measure potential difference easy. The resistance, okay, well, if you have a constant resistor, the resistor, then you could work out some of these calculations quite easily. We'll have a look at some of these calculations later on in the video. So what is a fuse? As I said before, that current generates heat. All right, so these thin wires that you can see in these fuses, okay, are certain thicknesses to allow certain current flow. If there's too much current, this wire gets too hot and it melts, which puts a break in the circuit, yeah, and stops the flow of current. So this is a way of safeguarding electrical equipment which costs quite a lot. You can put in a cheap little fuse here and you can burn these out and you can replace them very cheaply, and it protects the expensive electrical devices. Also for safety, to making sure that the current is flowing in the right direction and there's no short circuits. So let's have a look at a work example here. So in this case here, we're using this formula, P equals IV or VI, and we're connected to a 230 volt source. So there's our V value and a current of 4 amps. So all we have to do then is substitute in for 230 and 4 amps, and we get that the answer is 920 watts. Let's try this one by yourself. Pause the video, see if you can answer it, and come back to see how you go. Okay, so hopefully what you did is a simple substitution here. P equals IV or VI, whichever one you want. The current they said was 6 amps and the voltage 120. So we're looking at 720 watts. The next example is we're using a different formula. So part of it's just picking what information they give you. So we can usually work out if they give us 2 of the I and V or V and R or I and R, we can always work out the power. So here they want to work it out when there's current flowing and a resistor. Okay, so this is the formula we would use. Substitute in for the current, which is milliamps, is times 10 to the negative 3. Square that value, multiply it by 20, and we get 2 milliwatts. Okay, milli once again meaning over 1,000. Pause the video, give it a go, and come back to see how you went. Okay, so in this case here, we're using the same as the worked example, I squared over R. Substitute in for 20 times 10 to the negative 3 amps, and we're going to square that, and then we're going to multiply it by 50. This gives the value 0.02, and because we're using SI units, that's been in watts. So I think you could leave it like that unless you really wanted to express it as 20 milliwatts. So electrical devices do work, therefore power dissipation is the most important electrical feature. So we got things like iPhone chargers, okay, and the electrical devices usually show you the watts. They don't talk about voltages because it's assumed that, well, if you're using this plug, it's going to be 240 volts. So they usually talk about wattage, okay, or the power. And so we have an iPhone charger here with 18 watts, and this one has 30 watts. So which one do you think would charge the iPhone the fastest? Well, the 30 watts would almost do it twice as fast. So just in the summary, power is a rate at which energy is transferred and transformed into a circuit component. So each component is going to have a different power because it has a different resistor, and so that's important. So it'll have a different potential difference across it as well. And then we can rearrange the power formula to be into any of these forms, whichever one we feel is relevant. What we also realize is that it is the most important feature, and most electrical devices will have the voltage and the power written on it. And so this kettle here, if we're buying a kettle, if we want it to do it faster, we're going to need a larger powered kettle. This one here, okay, will tell you that it's a 10 watt. We talked about the iPhone chargers and the importance, or if you want to charge your phone faster, buy a more powerful adapter. Okay, so hopefully we learned a little bit about power. We also spoke about how electrical engineers increase the voltage to transfer current from one place to another. Well, I shouldn't say current, electrical energy from one place to another in order to stop heat loss.